Okay. All right. Hi guys. In this session, we are going to discuss about Thevenin's theorem. Okay. Where it is used. What's the application of Thevenin's theorem? Right. So we can use Thevenin's theorem for the network consisting of both AC and DC. So our network may be either AC network or DC network. Right. Then we have both independent and dependent sources that may be either current source or voltage source. So our sources may be independent sources or dependent sources, right? So we can apply this theorem when our sources may be independent or dependent sources, right? And third, our source may be a voltage source or a current source, right? Okay, so this may be voltage source or current source. Then what about our element? The network consisting of only bilateral elements, right? Bilateral elements such as resistance, inductance, and capacitance. So it should containing only bilateral elements, symbol for resistance or inductance or capacitor, right? Then we can apply Thevenin's theorem, right? So Thevenin's theorem is applicable for the network consisting of both AC and DC. The sources may be independent or dependent. That may be current source or voltage source. And the elements should be bilateral elements such as resistance, inductance, and capacitor. So this is a condition on network. Then what is the use of Thevenin's theorem? We can use Thevenin's theorem so as to evaluate voltage, current, or power across any element, right? So by using this theorem, we can evaluate voltage, current, and power across any element within the network, right? So first, these are the conditions on network elements, and this is the use of Thevenin's theorem. So simply, we can construct a network, right? This is our network. The network is a linear network, that is linear two terminal, right? The network should have two terminals, this terminal 1 and terminal 2. Let me mark it as A and B. And the elements within the network is bilateral elements, right? So this box will represent the network. It consists of linear bilateral elements and both AC and DC voltage sources that may be independent or dependent, right? That may be either current source or voltage source. And element should be a bilateral elements like resistance, inductance, and capacitors, right? And we can connect the load at this terminal AB, that right. So let this is a resistive load indicated by RL, and the load current is indicated by IL. In the case of a DC network, we can mark the load voltage as VL, right? Now what is load power? Power across the load, that is equal to load current square multiplied by load resistance, right? This is applicable for both AC networks also, right? So this is the basics of Thevenin's theorem, right? So we have three cases, right? First case is the network consisting of only independent sources, and second case is the network consisting of both independent and dependent sources, and the third case is network consisting of only dependent sources, right? Now we can discuss the three cases individually, right? Okay. Okay, I'm discussing the each cases individually. So we have case 1. In this case, all sources that may be current source or voltage source, right? Either AC or DC. So all sources are independent, right? So we have only independent sources in the network, right? Okay. So we can represent an independent source by a circle, right? So this will represent a DC voltage source, or this may be a AC voltage source, or maybe a current source, right? So all the sources are independent sources. In this network, we can find Thevenin's voltage and equivalent resistance by making use of conventional method, right? So I am drawing the network. So again, we have linear two-terminal network consisting of bilateral elements, right? So this is our terminal A and B, right? In this terminal, we can connect any elements whose voltage, current, or power to be determined. That can be treated as a load, right? Okay. Now, this voltage, this open circuit voltage, that is called Thevenin's equivalent voltage, VTH, or V open circuit voltage, right? Or simply VAB, the voltage across the open circuit terminal. For evaluating VTH, what we have to do is we first disconnect the load, right? And determine the voltage across the open circuit load, right? So what we have to do is disconnect, right? Disconnect the load. Okay. Then you have to evaluate open circuit voltage. Evaluate open circuit voltage across the load, right? So first you disconnect the load and determine the value of voltage across that open circuit, right? Voltage across, evaluate open circuit voltage across the load, right? For doing this, what we had to do, we just disconnect the load and measure the voltage across that load, right? That open circuit load. Then we have to determine RTH, right? This is a step for determining VTH. For determining RTH, what we have to do is we just short circuit all the voltage sources and open circuit all independent current sources, right? So short circuit all voltage sources, right? Okay, this voltage source is independent voltage source, and in the circuit it may consisting of current source. So what we have to do, we open circuit all current source available in the network, right? Then you have to evaluate the equivalent value of resistance as seen from the load terminal. Then obtain equivalent resistance. In the case of AC network, we are replacing the term resistance by impedance, right? Impedance with respect to the load terminal, with respect to the load terminal. So for determining Thevenin's equivalent resistance, what you have to do is you just open circuit all independent current sources and short circuit all independent voltage sources. Then disconnect the load and determine the effective value of resistance with respect to the load terminal. Then we can draw the circuit, right, as a single voltage source whose value is given as VTH, right? Thevenin's equivalent voltage, VTH. And this is RTH. This is our terminal, open circuit terminal AB. And we can connect load at this terminal, right? Load RF. In the case of an AC network, Thevenin's equivalent voltage is an AC voltage, VTH. And we are replacing Thevenin's equivalent resistance by impedance, Thevenin's impedance at TH, right? And this is our terminal AB, where we can connect load, right? Now let us connect the load as said, right? Now we can evaluate. So by making use of Thevenin's theorem, the entire network can be replaced by a single network consisting of a single voltage source in series with a resistance or in series with an impedance in the case of an AC network. So this is the first method, that is our network consisting of only independent sources, right? Now, our second case, the network consisting of both dependent and independent. That is, network consists of both dependent and independent sources, right? This is the second case. So sources may be independent source or dependent source, right? In this case, what do we have to do to determine VTH and RTH? We can determine VTH, right? That is the voltage across the open circuit load. So this is the open circuit voltage, right? Across the load terminal, voltage across load terminal, right? Since this circuit consisting of dependent and independent source, while evaluating VTH, we can't do anything with the dependent sources. We should retain the dependent sources, whether dependent current source or voltage source within the network while evaluating VTH. Since we have no options to short circuit or open circuit dependent sources. So while doing problem, you should retain this source within the network while evaluating VTH. So what you have to do is we just open circuit the load and evaluate the voltage across that open circuit condition, right? Then second, we have to determine RTH. RTH is equal to VTH, Thevenin's equivalent voltage, divided by ISC, right? What is ISC? ISC is the short circuit current across the load. So we have the network, right? Then what we have to do? We just short circuit this load terminal. So this is short circuit, and this current is called short circuit current, right? So first you evaluate VTH by open circuit the load, open circuit this load, and obtain the value of VTH, right? Then what we have to do is just short circuit the load and calculate the value of ISC, right? Then you can find RTH as VTH divided by ISC, right? This is a second case. Now we have one more case. In that case, the network consisting of only dependent sources. That is, this is our third case, consisting of only dependent sources, right? In this case, we have no independent sources. We have either dependent current source, right, or dependent voltage source. So in this network, VTH, that is equal to 0. Similarly, short circuit current, that is also equal to 0, right? And we can evaluate RTH or ZTH. RTH, that is equal to VDC divided by IDC, right? So this is a method for determining the value of Thevenin's equivalent resistance when the network consisting of only dependent sources, right? Now, based on these three cases, we have to do some different problems that is applicable for gate and also for ECE, right? So the first question is a very simple question. I'm drawing a network, right? We have a two-terminal network. Okay, this consisting of bilateral elements and sources, that is linear two-terminal network consisting of bilateral elements and sources, right? Now, this is open circuit terminal. I am marking the value of voltage across this terminal as V. Now, connect a current source at this terminal. A resistance is connected here. Then, right, I'm connecting a voltage source, right? An independent voltage source, right? Now, let the values of this current source be 2 ampere. This be some 3 ohm resistance. So this is some 8 volt. The question is to determine the value of V for this network, Right. Options are given. Option A is 4 volt. Option B is 2 volt. Option C is 0 volt. And option D is indeterminate. Right. Indeterminate. These are the 4 options for this problem. Right. Now, let's just check what's the correct answer. Okay. Now, we have a linear network. We know that it consists of voltage sources, current sources, that may be AC or DC, may be independent or dependent, and bilateral element. Now, we want to determine this voltage V, right? For that purpose, we can apply Kirchhoff's voltage law for this loop, right? Okay. Now, this V, that is equal to voltage across this 2 ampere current source plus voltage across this 3 ohm resistance plus the voltage source, voltage of this source. We are moving from plus to minus, that is from higher potential to lower potential. So this value is 8. So this is equal to voltage across the current source plus voltage across this 3 ohm resistance is 3 into the current passing through this 3 ohm, that is 2 ampere plus 8. So this is equal to V2A plus 6 plus 8, that is 40. This much volt. Okay. So this is a value of this voltage V. But the value of voltage across this current source is unknown. That may be any value. By using this data, we can't determine the voltage, the value of voltage across this current source. So 14 plus an unknown quantity, that's a variable quantity. So we can't determine the value of V. So the answer is D. That is, the value of V is indeterminate, right? A simple problem, right? Now, we can do another problem so as to determine Thevenin's equivalent voltage. For that purpose, let us consider a circuit which comprises of a voltage source, a resistance drawn here. Here, I have an dependent voltage source. No, dependent current source, right? Current source. Okay, right. Now, I'm drawing one more resistance here. Okay. Now, marking this voltage as Vx, right? So this current, this is an dependent current source, and this current will depending on value of this voltage Vx. This is given as Vx divided by 4000. Now, the value of this voltage source, that is given as 4 volt. This resistance is 2 kilo ohm and this resistance is 3 kilo ohm. Right. Our question is to determine VTH. That is the question, and also determine Thevenin's equivalent resistance. Okay. Actually, this is a previous year gauge question. Options are given, and I'm not writing the options here. Right. So this is our circuit. Okay. Now, first we need to determine VTH. VTH. Right. For that purpose, what we have to do? We open circuit the load. VTH is same as the open circuit voltage across this terminal. That is equal to Vx. Right. Since this is open circuit, so the voltage at this node is same as that of Vx. Right. And here is an open circuit. So the current flowing through this resistance is 0 ampere. No current will flow through this resistance of 3 kilo ohm. So we can apply KCL at this node. Now, apply Kirchhoff's current law at this node, right? I am assuming this current is outgoing current. And this current, we know, this is incoming current, incoming to this node. All right, so we can write this current, there is a potential difference divided by 2K. So Vx minus 4, that is a potential difference. Vx minus 4 divided by 2K, that is divided by 2000, that is equal to incoming current. Incoming current is given as Vx divided by 4000. By simplifying this, we can obtain the value of Vx by taking the LCM and simplifying. So we have 2 times Vx minus 4. That is equal to Vx. By simplifying this, we will get Vx that is equal to 8 volt. Right. Now we determine the value of VTH. Now the next question is to determine RTH. Right. RTH. For determining RTH, what we have to do in this circuit? We have dependent sources. So there is no option for eliminate dependent sources. So we know RTH is equal to VTH divided by ISC, where ISC is the short circuit current across the load. So for that purpose, what I am doing is I am short circuiting the load terminal, right? Now short circuit the load terminal. So what this current is called ISC, right? And when this terminal is short circuit, what's the value of Vx? Vx is equal to 0. Since for a short circuit path, the voltage becomes 0. When Vx is equal to 0, what's the value of this current? This current is equal to Vx, 0 divided by 4000, that is equal to 0. So when we are short circuiting the output terminal, this current becomes 0, right? When this current becomes 0 means we can open circuit this, since no current is flowing. So I just open circuit this source, right? Now we have a circuit having only a single loop. By applying KVL, we can determine the value of ISC, right? So what is ISC? ISC is equal to 4 divided by total resistance, that is 2 plus 3K. So 4 by 5000. This is the value of ISC. Now we can determine RTH. RTH is equal to VTH 8 divided by 4 by 5000. By simplifying this, we will get this is equal to 10 kilo ohm. So this is the value of Thevenin's equivalent resistance, right? So we can draw the equivalent circuit that consisting of a voltage source in series with a resistance, and we have terminal here. Here we can connect the load. The value of this is 10 kilo ohm, and value of VTH that we determine as 8 volts. So this is our equivalent circuit. So the circuit consisting of dependent source, we have to use this method so as to determine RTH. That is VTH divided by ISC. ISC short circuit current. For getting the value of short circuit current, what we are doing? We simply short circuit the load terminal and evaluate the current ISC. Right. Okay, this is the second problem. This is also a previous year gate problem. Okay, now we can do a simple problem. I'm drawing a circuit. We have a source here, right? I'm drawing a resistance here. Now, another resistance. Here, I have a branch, a current source, an independent current source, parallel with a resistance, right? Now, we can connect one more resistance here, right? And this is our terminal. Here, I connected one more resistor. Now we can give the values. Let this be 12 volt, right? This be 12 volt battery. Okay. Now, what is the value of this resistance? That is 4 ohm. Let this be 2 ohm. This is 3 ampere. 2 ohm, right? 6 ohm and 3 ohm. Our question is to determine the value of current that flowing through this 3 ohm resistance, right? That's our question. Determine the value of current in this 3 ohm resistance. Okay, we can do this problem in several ways, but we are making use of Thevenin's theorem here, right? So before doing that, I'm using a simple concept. Here we have a current source in parallel with a resistance. So we can use current to voltage source transformation. So in a network, we have branch like this, a current source in parallel with a resistance R. This can be transformed to a voltage source in series with a resistance. Okay, so both of these circuits are equivalent. Here, the value of resistance is R. The value of voltage V is given as I into R. Okay, now by using this concept, I am replacing this branch by a voltage source in series with a resistance, right? So we can redraw this branch as a source in series with a resistance. The value of resistance is given as 2 ohm. Here the source is, we know current is 3 and R is 2. 3 into 2, that's equal to 6 volt. So this battery source have the value of 6 volt. Now our network will look like this, right? Okay. Now we want to determine VTH and ITH. For determining VTH, what we have to do? We just open circuit the load terminal. Right. Now we are given the polarity plus minus. This voltage is our VTH. Right. Okay. So since the load is open circuit, we are open circuit load. So the current flowing through this resistance become 0 ampere. That is, no current will flow through this 6 ohm. So the potential at this node is same as that of VTH. Now apply KCL so as to determine the value of VTH. So VTH means the voltage across this branch. This is a VTH, right? So we can say VTH, that is equal to this potential. We are moving from higher potential to lower potential. 6 plus 2 into the current flowing through this branch. Let this be I. 2 into I. This is the value of VTH, right? Now we have only one loop here, right? We can apply Kirchhoff's voltage law. Let this current be I. So 2I, right? Plus 6 plus 2 plus 4 into I minus 12, that is equal to 0, right? So it's a value 4 plus 2, 6I plus 4, 6 plus 2, 8, 8 minus 12, that is minus 4. 6I minus 4 is equal to 0, or I is equal to 4 by 6, that is equal to 2 by 3 ampere. That is the value of current, right? Now, by using this equation, we can obtain VTH, that is equal to 6 plus 2 into 2 by 3, that is equal to 6 plus 4 by 3, right? Two I plus 6 plus 2, no, this is 2 into I, right? 2I, okay, plus 4 into I, that is 2. So we have 2 plus 2, 4 plus 4, right? 8I. So we can get 8I minus 12, 6 minus 2, minus 6 is equal to 0. Or I is equal to 6 by 8. That is equal to 3 by 4. 3 by 4. Okay. 3 by 4 plus 6. 2 plus 6. Or we can do this as we have only one loop, right? So for obtaining the value of current, we can directly the potential difference, that is 12 minus 6 all divided by total resistance. 2 plus 2, 4 plus 4, that is equal to 8. So 6 by 8. 6 by 8 means 3 by 4 ampere, right? Now the value of VTH, that is equal to, I already told, this is the value of VTH. VTH, that is equal to 6 plus 2 into this current. That current is equal to 2 into 3 by 4. That is equal to 6 plus 3 by 2, right? That is equal to 1.5 or 7.5 volt. That is the values of Thevenin's equivalent voltage, right? Now we need to determine the value of RTH, right? So as seen from this terminal, this is our load terminal. Okay, RTH. For that purpose, we just short circuit this voltage source. Also short circuit this independent voltage source. Now, this 2 and 4 is in series. So we can replace this by 6 ohm, right? Now, this 6 and 2 are in parallel. That is in series with 6 ohm. So we can write RTH, that is equal to 6 parallel 2 plus 6. that is equal to 6 into 2 by 6 plus 2. That's 8 plus 6. That is equal to 12 divided by 8 plus 6, right? Or 4 by 2. No, 3 by 2 plus 6. That is also equal to 7.5 ohm. So we got the value of RTH and VTH. Now draw the equivalent circuit. Right. So we can draw the equivalent circuit 7.5 volt. That is VTH. That is 7.5 ohm. And we have a resistance of 3 ohm. This is our load. So this is our load current IL. Right. Our question is to determine the current flowing through this 3 ohm resistance. Right. So this IL, that is equal to 7.5 divided by 7.5 plus 3. That is equal to 7.5 divided by 10.5. Approx 0.714 ampere. This is the correct answer. Right. Okay. So this is a problem that consisting of only independent source. So here we used a simple trick, that is a conversion of current source to voltage source, right? Or we can directly do by considering just a current source also. Okay. Now consider another problem. Okay. I'm drawing a circuit. Let this is 50 volt, right? We have a resistance here, another resistance here, and a voltage source. Then the value of this voltage source is 25 volt. Right, 50 volt, 25 volt. Then let this be 10 ohm and this be 5 ohm. Right. Now I'm giving a terminal here A and this be B. Our question is to determine Thevenin's equivalent voltage with respect to this terminal AB and equivalent resistance. So we have to determine VTH, that is equal to VAB, and also we need to determine RTH. Right. Okay. So it's a very simple circuit. We have only one loop. This is our loop. So this is the current flowing through this loop, right? So what's the value of VAB? Right. So from this loop, we can determine its value of this current I. Okay, so I is equal to potential difference, that's 50 minus 25, right? 50 minus 25. Divide by total resistance, 10 plus 5. That is equal to 25 divided by 50. Or answer is 5 divided by 3 ampere. This is the value of current in this loop, right? Now, we want to determine VTH and RTH with respect to this terminal. So, what is VTH? That is equal to VAB. So, we can consider this loop, right, for determining the value of VAB. So, VAB, that is equal to 5 into this current, that is 5 by 3, plus this voltage, 25, since we are moving from positive terminal to negative terminal. So, that is equal to 25 divided by 3 plus 25. So, this numerically equal to some 33.5. Right. That is the value of VTH, 33.35 volt. This is the value of VTH. Right. Now, we want to determine the value of RTH. Right. So, we got VTH. Now, what is RTH? For determining RTH, what we have to do? We have voltage sources. So, first short circuit, this voltage source, and also short circuit, this voltage source. Okay. So this is our equivalent circuit, and we are seeing RTH as from this terminal, right? AB. So this is equivalent to two resistance. So this resistance 10 ohm in parallel with this is 5 ohm, right? 5 ohm. Okay. And this is our point A, terminal AB. So this 10 and 5 are in parallel. So RTH, that is equal to 10 parallel 5, or 10 into 5 divided by 10 plus 5. Okay. So 50 divided by 50. So the value is equal to 10 by 3. That is 3.333 ohm. So this is the value of RTH, right? Okay, so we can draw the equivalent circuit with respect to the terminal AB as, so first I drawn the voltage source here, then RTH, and we can the terminal A, B, the value of VTH, that is 33.35 volt, and this is 3.33 ohm. So this is our Thevenin equivalent circuit, right? Okay. Now we can do one problem that consisting of AC sources and impedance, right? Okay. For that circuit, we need to determine Thevenin's equivalence. So consider the circuit which consisting of an AC source, right? Then we have a resistance, a capacitance, right? Here a resistance, an inductance, then an inductance and capacitor, right? This is our terminal AB, and we need to determine the value of Thevenin's voltage and Thevenin's impedance with respect to this terminal. This is VTH, right? Now we can give the values. The value of the source is 15 at an angle 0 degree, this much volt, right? And this is 3 ohm. And the value of this capacity reactance minus J4 ohm. Since this is capacity, so this minus sign came. The value of this resistance, let 4 ohm. This is J6 ohm and J5 ohm and minus J4 ohm. So the values of capacitance and inductance is given in terms of impedance, capacitive reactance or inductive reactance side. So this is a circuit. We need to determine VTH with respect to terminal AB, right? So what do you have to do? For determining VTH, this terminal is open circuit, right? Open circuit. So no current will go through this element. So the current in this element is 0 ampere. So this voltage is same as VTH or VAB, right? So this voltage, the voltage across this element will represent VTH, right? So we can say VTH, that is equal to this impedance 4 plus J6 multiplied by current passing through this. Let this current be I, right? So and the value of I, what's the value of I? 50 voltage, a 50 angle 0 voltage divided by total impedance, right? So we can write this as 4 plus J6 multiplied by 50 at an angle 0 divided by total impedance, that is 3 minus J4 plus 4 plus J6, right? Now simplify this expression, then we will get this is equal to 4 plus J6 multiplied by 50 at an angle 0 degree, all divided by 3 plus 4, 7 plus 2J, right? This is numerically equal to 49.5 at an angle of 40.35 degree. This is the value of VTH, right? Now we need to determine the value of ZTH with respect to this terminal. For that purpose, what we have to do is, this is independent current source. We just short circuit this independent current source, right? Okay. Now they find the equivalent resistance. So this branch is in parallel with this branch, that is in series with this branch, right? So we can write ZTH, that is equal to this impedance 3 minus J4, that is in parallel with this branch, that is 4 plus J6, that is in series with this, that is J5 minus J4. Okay, J5 minus J4, that value is equal to plus J. So this is the value of ZTH. By simplifying this, we can get this as 3 minus J4 multiplied by 4 plus J6 whole divided by sum of these two. 3 plus 4, 7 plus 2J plus J. By simplifying this, we will get the value of ZTH as 4.83 at an angle of minus 1.13 degree. This much ohm. Right. So we can draw Thevenin's equivalent circuit as, okay, we have an AC source, right? This value is given as 49.5 at an angle 40.35 degree, this much volt, and we have a series impedance. This is our load terminal, right? The value of series impedance is 4.83 at an angle of minus 1.13 degree. This much ohm, and here we can connect load, right? Either impedance or resistance, right? This is our equivalent network, right? Okay. Now we can do a problem which consisting of a Weissen's bridge, right? And we know that the condition under balanced condition, the galvanometer show zero deflection, right? That's the principle of a Weissen's bridge. Okay, let us solve an unbalanced Weissen's bridge. For that purpose, first I am drawing the circuit. Okay, so we have a source, let a battery source, right? Now I am drawing a distance grid. A branch here, another branch here, another branch here, another branch. So this is our distance grid, right? Now I am drawing a resistance here also. Okay. Now let us give the values of these elements. Let this is a DC voltage source, numerically value 100 volt. This is 10 ohm. This is 15 ohm. This is 6 ohm, 8 ohm, 5 ohm. Then the current in this 5 ohm resistance be I. And question is to determine the value of I. Options are given. A, that is I is equal to our question, right? A 0 ampere. 0 ampere happens only when this bridge is in balanced condition. And choice B is given as 1 ampere. C is given as 0.194 ampere. And the option D is 2 ampere. Right. Okay. Now, this is our problem. We have Weissen's splits. Right. Okay. So, what is the condition for balance? So, we can say this is R1. I'm writing this is R2. This is R3. This is R4. So, under balance condition, we can say R1 by R2, that is equal to R3 by R4. If this condition is satisfied, then no current will flow through this 5 ohm resistance. So let us check. So we know the value of R1 is 10, R2 is 15. So 10 by 15, that's equal to 2 by 3. This is equal to R1 is equal to, that's equal to 3 by 2. So this is not equal to R1 by R2. So the bridge is not balanced. Right. So the current will flow through this 5 ohm resistance. Right. So we can solve this by making use of Thevenin's theorem. Right. Okay. Now I am marked. I am open circuit the load. So this 5 ohm resistance is open circuit. We are giving this point as A and this point as B. So this voltage is called Thevenin's equivalent voltage or open circuit voltage. Right. Now we have to determine the value of Thevenin VAB, that is VAB, that is equal to Thevenin's equivalent voltage VTH. Now I am going to redraw the circuit. So we have 100 volt, right? Now we can draw this as this point is our A. This is 10 ohm, 6 ohm, right? Now this branch that can be drawn as 15 ohm, 8 ohm. This is 15 ohm. This is 8 ohm. This point is B. Right. So these both circuits are identical. Right. From this circuit, we can determine the value of VTH. So this is a value of VTH, open circuit voltage across that terminal. Right. Now, VAB, that is equal to VA minus VB. Right. This is same as Thevenin's equivalent voltage. What is VA? VA is the voltage across this 6 ohm resistance, and VB is the voltage across this 8 ohm resistance. Right. So we can say VA, that is equal to 6 into I1. Let I1 be the current flowing through this branch, and I2 is the current flowing through this branch. Right. So this is numerically equal to 6 into I1 is, this is 100 volt, that is in parallel with this net resistance. So 100 divided by 10 plus 16, that is a value of I1. 100 divided by 10 plus 6, that is 16. Right. So this is equal to 600 divided by 16. Now the value of VB, this voltage, that is equal to 8 into I2. That is equal to 8 into I2 is 100 divided by 15 plus 8. That is equal to 23. Numerically is equal to 800 divided by 23. So the difference of these two will give the Thevenin's equivalent voltage VAB. So that is equal to, the value can be found as, this is equal to, VA is equal to 37.5 volt, and this is equal to 34.78, this much volt, right? So VAB, that is equal to 37.5 minus 34.78, that is equal to 2.717 volt. So this is the Thevenin's equivalent voltage, right? Now we want to find Thevenin's equivalent resistance. For that purpose, what we have to do? We can just short circuit the source, right? So this become our equivalent circuit, right? Equivalent circuit. Okay, this is equivalent to, this 10 and 6 are in parallel, and this 15 and 8 is in parallel. So we can write RTH is equal to this 10, and we are evaluating RTH with respect to this terminal. So 10 is parallel with 6, right, plus 15 parallel with 8. So this is equal to 10 into 6 by 16 plus 15 into 8 by 23. That is equal to, numerical value is 8.974. You can calculate this. Now draw the equivalent circuit. Draw the equivalent circuit means I'm drawing the equivalent circuit, the voltage. Okay, right. Then we can connect load here. The value of Thevenin's equivalent voltage is 2.717. RTH is 8.97. And we can connect the load of 5 ohm here. Right. So from this expression, we can determine the load current IL. That is current flowing through 5 ohm resistance. If that is equal to IL, that is equal to 2.717 divided by 8.97 plus 5. This is equal to 0.194 ampere. Right. So this is the current flowing through that branch of resistance bridge. Right. Okay. In the next class, we will discuss more problems related to Thevenin's and Norton's theorem. Okay. Thank you. Bye.